What is up, my mathematical mischief makers? In this video, we're going to learn how to factor trinomials with a leading coefficient of 1. So, a trinomial is a polynomial that has 1, 2, 3 terms in it. Remember, terms are separated by addition and subtraction. And a leading coefficient is the coefficient on the monomial of largest power. So, the largest power here is 2. And so, this is my leading term. And it has a coefficient of 1, so that's the leading coefficient. So we're going to first start off with factoring trinomials in this manner right here. So how do you do that? Well, what we do is we want to write an equivalent form where we undo the foiling. Remember, foiling, first, outer, inner, last. So I want this right here to be an x squared. And so when I do the f in FOIL, that's got to be x times x. That's really the only way to get an x squared right here. All right. So the next part is what confuses people, and so that's why we're going to go through many examples to try to eliminate that confusion. So it's all about this number right here, this 10, this constant coefficient. I want to figure out what the factors of this thing are that can add or subtract to give me 3. So for example, the factors of 10 are 1 and 10, 2 and 5, 5 and 2, 10 and 1. Now, it really doesn't matter what order we do these in, and so what's nice is you don't have to list every single one. The list is redundant thanks to the commutativity of multiplication and addition. So, can I add or subtract 1 and 10 to get me 3? The answer is no, because that's either going to be an 11 or a 9. So, by process of elimination, it's 5 and 2. 5 minus 2 is going to give me 3. So we got a 5, we got a 2 right there. Okay? And I need that to be a negative 3. And so I need this 5 to be negative right here, and I need this 2 to be positive. Right? And that is our answer. Now, what's nice about these problems is you can always check your work. Let's go ahead and check our work. FOIL, right? We're going to use the distributive property of the product of two binomials to make sure we get this right here in the end. So now let's check. Alright, x times x, that is the f in FOIL, so that's x squared. We have x times 2, that's the outer, so plus 2x. We have so let's call that O. Let's do the I in FOIL, that's negative 5x. And then the L in FOIL is negative 5 times 2, which is negative 10. So when I simplify this and I gather like terms, that's the only x squared piece right there. Positive 2x minus 5x is negative 3x, and negative 5 times 2 is negative 10. So we can see that we get the answer that we started with. We know that we're pretty confident that that's the answer right there. All right, so I factored it, meaning I've broken it down into its smaller components. So now we're going to factor x squared plus 21x plus 108. Right? So I've made this problem on one hand easier, on one hand harder, on purpose. Alright? So what I need to do is I need to find the factors of 108. Alright? So when you are just starting off with these things, you probably just want to go through and list it. Just get the hang of doing this. It becomes automatic as you practice more and more and more. Many people can just look at these trinomials once they get the practice and the experience, and they can just basically do them in their heads. And that might be frustrating to some of you that are like, how the heck can they just do that right away? Probably because they've spent many, many years doing this stuff and practicing. So that's really the only way you're going to get good at math is you practice, 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 just like any other skill. So let's go ahead and off to the side here, write down the factors, not necessarily the prime factors, but all the factors that make up 108. So I have a 1 and a 108. I have a 2 and a 54. I have 3. 3 will go into there. And I know 3 goes into there because the sum of these digits add up to 3. And remember, if the sum of these digits, 1 plus 0 plus 8 is 9, if that sum is divisible by 3, then this whole number will be divisible by 3. That's a nice little trick to seeing if 3 goes into these numbers that we have here. So 3 goes into 108. 3 goes into 10 3 times with 1 left over. 3 goes into 18 6 times. All right, 4 goes into there. It goes in there, I believe, 27 times. All right, 5 doesn't go into 108 because it does not end in a 0 or a 5. Let's see, 6 will probably go in there. 6 goes into 10 once. With 4 left over, 6 goes into 48 8 times. So I get 6 and 18. 7 I don't believe goes in there. 8, let's see if 8 goes in there. 8 goes into 10 once with 2 left over, but 8 does not go into 28. And so actually 8 does not go in there. 9 will go in there. I believe we can verify that that would be 12 times. 10 does not, because this does not end in a 0. 11 does not. And then once I get to 12, I'm back at one of my factors that I already have. So I have a list of all the factors that are going to add and subtract, or I'm sorry, that are going to multiply to give me 108. And now I want to find the magical combo that's going to add or subtract to give me 21. So let's write out what our answer is going to look like. Since the leading coefficient is 1, there's only one way to get x squared, and that is x times x, when I'm trying to pull this apart and break it down and factor it. All right. So which of these is going to add or subtract to give me 21? Not that one, not that one, not that one. This is either going to give me a 39 or a 33. This will give me a 31 or a 23. As we go down the list, now I said when I started this problem that I've made it easier because if these are both positive right here, there's no negatives involved, so I don't have to worry about any sort of negative right here. The problem that I had up here, this was a negative and a negative, so I needed them to add up to give me a negative number, but I also needed two numbers to multiply to give me negative 10. And so one negative and one positive number, when those are multiplied together, I get a negative. So negatives kind of make things a little bit more interesting and a little bit more involved. You have more to pay attention to. But here, since these are both positive, I just know that I just need a positive number here and a positive number here. And this is the answer right here, 9 and 12. 9 plus 12 is going to give me 21x, right? And then 9 times 12 is going to give me 108. So this is my answer right here. And as always, you should check your answers. All right, FOIL this out. And this is just good practice in foiling and making sure that you get this right here. All right, this next example, I'm doing this on purpose with a capital Q because I've also found that when students see a new variable that's not x or t, that completely throws them. All right, this happens to be a Q. The principles and the ideas are the exact same thing that we've just talked about. So leading coefficient of 1 means that the only way to get a Q squared is if we have Q times Q. All right. And then we're going to list the factors of 24 and try to find the ones that add or subtract to give me 10. So 1 and 24. And as we go through them, let's figure out which ones we get. There's no point in listing all of them if something in the middle is actually the one that works. So 1 and 24, that's not going to add or subtract to give me 10. 2 and 12. All right. Now, this seems like it's going to be a candidate because 12 minus 2 is 10. But the problem with this is, and this is where the sign comes in, I have a negative right here and a positive right here. So I want two numbers that add to give me a negative, but multiply to give me a positive. All right. Now, if something's got to be negative and something else has got to be negative in order to multiply to give me a positive number right here, right? And the reason why these both have to be negative is because that's positive. The reason why we have any negative involved is because there's a negative in front of this Q to the first term right here. All right, so that begs the question, why doesn't 12 and 2 work? Well, let's write it up here, 12 and 2, all right? If I FOIL this out, I'm going to get a negative 2Q minus 12Q, and that's going to give me a negative 14Q. So while these do multiply to give me a positive 24, when I gather the like terms when I FOIL this out, I'm going to have a negative 2Q minus 12Q in the middle, and that's going to add up to give me negative 14Q, not negative 10Q. So this one seemed like it was going to work, but it doesn't work. This first one didn't work either. All right, 3 and 8. All right, do 3 and 8 work? And the answer is no, because 3 plus 8 is 5, 3 minus 8 is, 3 plus 8 is 11. That was embarrassing. 3 minus 8 is 5 or negative 5, and so that's not going to give me a 10 right there. And so cross your fingers that the last set of factors work, and they do. if I put a 4 here and a 6 here, negative 6q, the O in FOIL, minus 4q, the I in FOIL, is going to give me negative 10q, and negative 4 times negative 6 is positive 24. And so took a little bit of work. There was something that was rather deceptive right here. Looked like that was going to work, but it didn't, right? But we still got the correct answer in the end. That's why it's so incredibly important to check your answers. Okay, so we have this trinomial right here. It has a leading coefficient of 1, which is the whole theme of this video. I've changed my variable to t because why not? I like to write my t's with a little foot down here just to make them look different than pluses. Personal preference. I'm doing this problem because this actually has a special name to it. So let's just go ahead and do this problem and see what we get in the end. So what are the factors of 49, my constant coefficient? Well, there's 1 and 49. Those are not going to add or subtract to give me negative 14, so I move on. 2, 3, 4, 5, 6, none of those numbers go into 49. The next set is 7 and 7. And then I've reached this point where if I write the next ones, it's going to be 7 and 7, 49 and 1. So this is my whole entire list now. All right, so I hope that this is the answer. Now once again, I have a negative right here and a positive right here. So again, the first and only way to get a t squared right here is if I have a t and a t. All right, and 7 and 7 are my only hope, and they have to be negative and negative right here. Pause the video right here and make sure you understand why I just put 2 negatives right here. All right, assuming you paused the video, hopefully you got the answer. If you didn't, that's fine. That's why we're here. But the reason why I put 2 negatives here is, first off, there's a negative right here. So something's got to be negative. But this one's positive. So the only way I can get a positive 49, and with 1 negative involved, is if 2 negatives are involved. All right, and so since I know that 7 and 7 are going to add up to give me 14, this is the answer right here. Okay? And we can FOIL this out and we can check. T times t is t squared. Negative 7t minus 7t is negative 14t. That's the O and the I in FOIL. Negative 7 times negative 7 is positive 49. All right, so that's our answer. We could box it up like we like to and move on, but I want to point out that this is t minus 7 squared. Right? It's something times itself. When something is multiplied by itself, we square it. And this is what we call a perfect square. It's something times itself. It's a perfect square trinomial. So one of the keys and one of the tricks that people use when they look at something and they want to factor it is they look for stuff like this. These are special trinomials that factor a certain way. And so if you have something that looks like this, x squared minus 2ax plus a squared. All right? If you have something that looks like this, this will factor as x minus a squared. Okay? And if you FOIL this out, you can see why. Because you have x times x is x squared, negative ax minus ax, O and I in FOIL give you negative 2ax. Those are like terms. Negative a times negative a is positive a squared. All right? So this is a special form. And we can see that this problem that we were working on fits this sort of pattern because I had 7 squared. Hopefully we recognize 49 as a perfect square. It's 7 times 7. So the question is this number right here 2 times the square root of that number? And it is. If this is 7 times 7, if a is equal to 7, then if this is going to be a perfect square trinomial, then this had better be 2 times 7, which it is right here. 2 times 7 is 14. All right, so this is one version of the perfect square trinomial if there's a negative involved. And we also have, and we can show in a similar fashion, that x squared plus 2ax plus a squared, that's going to wind up factoring as x plus a quantity squared, which we can verify with FOILing. All right, so these are things that, of course, you don't have to recognize these, but these are shortcuts where if you see something where this is a perfect square on the end, and this is 2 times the square root of this perfect square, then you got yourself a perfect square trinomial. All right, as long as we're doing examples, we might as well do another one. We got y squared minus 9. Now, what may be confusing about this is we don't have a y in the middle. I mean, we do. It's actually y squared plus 0y minus 9. Remember, 0 times whatever is 0, so there you go. All right, so let's write down the factors of 9. We got 1 and 9. Those are not going to add or subtract to give me 0, so we move on. 2 doesn't go into 9. 3 does. 3 times 3. You might be thinking to yourself, ooh, maybe this is one of those perfect square trinomials like Max just talked about up here. But it's not, because we don't, so even though 3 times 3 is 9, first off, that's not a positive right there, like we need each of these to be up here, right? So it's not even a positive number, so we can move on from there. But also, this is not 2 times 3 in the middle right here. This is not a 6, this is a 0. All right, but this is still factorable because, again, the only way to get y squared is if the f in FOIL is y times y. All right, and now if we have any hope of getting 0, we have to have a plus 3 and a minus 3, right? Negative 3y plus 3y, those cancel out, those sum to 0y, and positive 3 times negative 3 is negative 9. All right, so this is the answer, and as a matter of fact, this also has not a perfect name, this has a special name. It's called a difference of squares. All right, the reason why it's called that is because there's a difference right here. Difference means subtraction of squares. Y squared is a perfect square, it's y times y, and 9 is a perfect square, it's 3 times 3, it's 3 squared. And so the rule for factoring these is if you have x squared minus a squared, a difference of two perfect squares, these always factor as x plus a times x minus a. And I can't tell you how many times in algebra or trigonometry or even calculus and even differential equations when students look at this and they just freak out and they freeze. They need to factor something like this and they don't know how to because they've just simply forgotten the fact that this is what we call a difference of squares and it has this nice pattern of factoring. Hey, you know what? We might as well do another example. We got x squared plus 2x plus 9. We've already factored 9 up here. We got 1 and 9. Those are going to either add up to 10 or subtract to 8. So that's not going to work because there's a 2 there. We got 3 and 3. Those are going to add up to 6 or subtract to 2. Or I'm sorry, subtract to 0. That's not going to give me a 2 right there. And that's my list. I mean, I guess if I wanted to, I could swap the 3's, but that's not going to matter. I could do 9 and 1, but that's the same problem as 1 and 9, right? So what do? The answer is we don't do anything. So sometimes we have trinomials like this, and it doesn't factor nicely across integers like we want it to. All right? Every single problem that I've done so far factors nicely across integers, nice whole counting numbers, right? This one doesn't. Now, you're going to learn how to do stuff with this later on when we want to solve equations and set this equal to something and solve. But for right now, as long as we're factoring trinomials, this actually doesn't factor nicely. And so we would call this prime. There's nothing we can do to this. There's no nice factorization as far as integers are concerned. And so with something like this, we call it prime and we move on. Now this next problem is not really a curveball, but it sort of is. Now this is certainly has a coefficient of 1, the leading coefficient of 1. It's not really a trinomial because there's a 0x to the 4th, there's a 0x cubed, there's a 0x squared, there's a negative 256x, and then there's a plus 0 right here. So this doesn't really look like something that we've dealt with, but I wanted to throw this in there because oftentimes I know people get frustrated with math and they learn something and they maybe even get the hang of it, and then something like this pops up and then you're like, well, what do I even do? I don't even know, right? So every single problem that we've done so far in this video, there's nothing that I could pull out of everything. There's no common factor, right? In this problem there is, because if I look at x to the 5th, which is x multiplied 5 times together, and I look at this right here, the number 256 times x, there's actually a common factor of x. And so one of the first things you want to do is look for something like that, a common factor. If I use my distributive property, I could multiply this back in. X times x to the 4th is x to the 5th. x times negative 256 is negative 256x. So that's all good and legal. Now, again, this doesn't really look like something that we've done because every single thing had a highest power of 2. But if we look, notice that x to the fourth is x squared squared. So that's a perfect square right there. And that 256, well, that's 16 squared. And so this is one of these things that I think is so important to try to recognize. It's a difference, subtraction of two perfect squares. All right? So remember the pattern of factoring differences of squares. If it's a thing squared, it's a thing and that thing. Right? This thing happens to be x squared. And so what I'm going to do is put an x squared there and an x squared there, because that's the thing that's being squared right here. Right? Now if it's an a squared, a minus a squared, well, my a in this case is 16, because it's minus 16 squared. And so I would put a plus 16 right here and a minus 16 right there. And there we go. All right? Very tempting, if you've been following along so far and you get it, to box it up and say, you know what, that problem took a long time. I even broke a sweat because I saw a power 5 there and I freaked out, but Max got me through it. Thank you very much. But that's not the answer, because we still have a difference of squares right there. It's a smaller difference of squares, not smaller, it's a different difference of squares. All right? Now this one is actually prime, and I encourage you at some point to convince yourself that this does not factor. There's no technique of factoring that I can do for this thing across integers. This one does factor because now I have x squared and 4 squared, and they're being subtracted. And so that is yet another difference of squares. X right there, plus 4 minus 4. Now, what I think would be a fantastic exercise for you to do is to check your work. FOIL this out. Use the distributive property here. Distribute your x back in here. Make sure that when you multiply all this nonsense out, you get x to the fifth minus 256x. It's a fantastic exercise in using your distributive property. Now remember, folks, if you got something out of this video, if this helped, if you enjoyed it, please subscribe to the channel. Please hit the like button on this thing. Let your friends know. And as always, if you are going to get good at math, if you want to get good at math, if you want to rid yourself of math anxiety and become the mathematical masters that I know you are, I want you to practice, practice, practice. And so the problems that I give you at the end, I always give you answers to them in the description below, so you can do these problems and check your work. This is the first step in mastering this stuff. If you need to, watch this video again. Watch my examples. In the comments below, ask me whatever questions you want to clarify. I'm happy to give you more problems to try. Now, I just want to point out that this last one right here, I agree, the leading coefficient's not 1, and that's not a squared. Maybe there's some sort of trick or pointer that I gave you that you could actually do something to this expression first before you factor it as a trinomial. Hint, hint. Anyway, thanks again for watching. Like this video, subscribe to the channel, tell your friends. I'll see you next time.